want to thank Floris for being a special co-host here, and we're gonna rock and roll. Slideshow. All right, can you guys see my screen? All right, so this month that we're in of October is Moisture Management Month. So the plan for the year was to kind of talk about moisture management. Moisture management as a big topic is a very big topic in that all buildings need to survive, they need to shed water, they need to be there for a long time. So that first image of the hands on top of that house to protect it is kind of like what our goal is of the basics of a shelter. All right, so thank you to House Accelerator. My name is Kevin Brennan. I'm a passive house tradesperson. I also teach for the Air Barrier Association, and I'm proud to be a part of this community and share with everyone. All right, so everyone's got their game on. We're gonna just relax a little now. Listen to the ASMR of it raining outside. Nice and calm. Look at that building. It's in the woods. I didn't know that ads thing was going to pop up, but it does sometimes. And that building built 200 years ago out of logs and timber. What is it doing? Shedding water. It's heated. It's drying out. It's controlling vapor, controlling all the things we're going to talk about tonight. But I'm going to stop this because this goes on for 11 hours if you wanted to listen to this and relax to it. All right. All right, silly video. All right, so moisture management. When it rains, it pours, and the buildings we live in need to shed that water to keep the buildings operational. It also needs to keep them comfortable. If you've ever been caught out in a rainstorm, first thing that happens when you get wet, you get uncomfortable. As a fireman, when I get wet, it's not long until frostbite and everything comes in. So our houses need to be able to manage moisture. That's why we have roofs designed the way they do. Walls are vertical. Everything's governed by gravity and the physics of buildings. So what is moisture and how does it exist? It exists as a solid as ice. It exists as a liquid as water. And it exists as a gas. When it exists as a gas, it's in the vapor form, but it's also it could be existing as steam, which isn't very common in buildings, but it's also in the relative humidity of inside the air. So each molecule of air that's in the air has a certain amount of humidity into it. So the next kind of like basics of moisture management are moisture flows in 4 different ways. It flows with gravity, and that it goes down. It's governed by the weight of the moisture going down a wall, over a roof, shingle fashion. It also can act as it being sucked up against gravity through capillary action through certain materials such as concrete or brick, can wick through other materials that say some sort of fabrics or so. We also have moisture that moves through diffusion. That's the vapors going through the material, say the vapors going through a brick wall. And we have air transport, which to me is the big deal of kind of like managing moisture. So as we're talking about moisture, a lot of what I've learned in my career, I've had very great privilege of going to building science summer camp. In my first summer camp, I listened to Joe Lestibrick talk about why wood buildings rot. And he hit a moment with it where it was, aha. So when a tree falls in the forest, does it make a sound? I don't know, but it does. Does it make a sound? I'm not sure. But what happens when that tree falls, and why did the tree fall? The tree's dead. It hits the ground, and the ground is kind of moist because of the rain and the moisture and the dirt. And that tree is now being brought back into the fungal world. It's being eaten by slowly being wet for a long period of time. And that's slowly going to create topsoil with the leaves and the other branches, and it's going back to its organic state. So when something is wet for a long period of time, it's going to start degrading and falling apart. But if it's dry, it's going to last for a very long time. One of the great documents that helped me prepare for this presentation was the moisture control in new residential buildings. Joe has a way of describing information in the way he writes things that is just very methodical and could fill up the time. So this is a great piece of information for reference if you guys somebody wants to throw it in the chat, or when Floris is talking, I'll put the link in there. So my next mentor is my good friend, Terry Brennan. Terry Brennan, no relation. So blow a door guru. Everyone always asks, are you guys related? And we're not related, but he's a building science nerd. I'm a building science nerd. We've crossed paths on projects such as Cornell Tech and other things like that. But he was hired to do a guide called a moisture control, EPA guide to moisture control in buildings, construction, design, and maintenance. And it's a great technical document to understand how moisture is controlled and where it goes. So one of the key parts of that document is the red line test, the purple line test that you see here. So the first one on the right side is the blue test, right? So you would take a blue pen on a sectional drawing and you would draw out all in blue where the water is going to be managed. So at the fascia board and the drip edge over there, the moisture is going to drip off. When it hits the brick, it's going to hit the reservoir cladding of the brick, either absorbed or drip down. At the head of the window, it's going to hit the drip edge and it's going to flash off. It's going to shed water away. The roof itself is going to shed water on the top side of the roof membrane and then below the concrete. So you have all your lines and ducts adding up. If there are any gaps in those lines, that's where we need to clarify the detail, right? So everything's kind of shingle fashion. And then we go over to the left side, which is the purple line trace test in the document. And that's our air barrier. And the air barrier, a lot of people don't correlate with moisture management, but there's a certain amount of air that gets transported in the relative humidity of air that kind of can be perceived as a water leak in a building, or cause condensation, or cause such things as wood studs to rot, or plywood or sheetrock to get metal, to get moist and then deteriorate. So it's a great example. And this is that tenement of passive house kind of air tightness, that all the lines add up and that there are details for each one. And now systems. So the name of the presentation is systematic moisture management. And if you've heard me talk before, or ever, kind of like my religious kind of standpoint is find a system and stick with it. When I say stick with it, meaning just go with the entire manufacturer systems, or unless you have an oddball. So in my career, I've been lucky to be located close by 475, which distributes the ProClima product line. And it's from like the wall all the way up to the roof. You're able to install a watertight layer up the wall onto the roof and back down. Now that roofing system that you see up there is very European, and that it's a tile roof that we don't really do here in the US, but we are getting more and more popular in doing metal roofing and other more durable roofing systems. So it's about the system. So go with the system and stick with it. Where we run into trouble with buildings is condensation. Condensation happens on single pane windows, where we have our greatest experience with it, when it's high relative humidity and the glass gets cold and we can see our areas in there. A lot of times we talk about radiator placement. The building I'm in right now has big radiators underneath all the windows because we're throwing heat at the windows to avoid condensation. And what happens with condensation is that it's tricky in that it's in the air and we can't see it, we can't touch it. We can only measure it with certain specific devices to measure relative humidity. And when a molecule there is 86 degrees, it has large volume that the molecule can work in, and then it has 28% relative humidity there. If I then would reduce the temperature of that water air molecule, the relative humidity would increase. So it's the same molecule there, but I've now reduced it down. So the way I explain it in my training classes to contractors is that each one of those balloons that you see there have a certain amount of like blue ping pong balls in them that represent moisture or the relative humidity inside those balls. Then we have a molecule there at 70 degrees, 50% relative humidity that's on the inside, very happy, very stable. And then we hit a cold surface. When we hit the cold surface, now the temperature of that air reduces drastically and then condenses all the way down. And now that air is really saturated and we have it in the dew point. So very kind of like intuitive way to explain what happens inside the wall or at the glass. Now, at the glass, it's not so much of an issue in that it'll evaporate over time. But if that's happening closed inside your wall, you're going to have damage over time, no matter if it's a wood frame building or masonry building. An example of dew point. Dew point is something that can be measured, and it's relative to the relative humidity in the air, which is kind of important. So this is from Proclima's website, and at Proclima's website, it explains in this in this diagram that more moisture is transported through a 1 millimeter gap, which is just a butt of a sheetrock, into a wall assembly 1,600 more times than through the material. So you'll have more water damage that'll happen through gaps and cracks and imperfections in the air barrier than will go through the material itself. So airtightness is a great way to moisture proof your building. This is vapor pressure going from high pressure to low pressure. When we talk about materials, some materials are vapor open, some materials are vapor closed. And then the permeability of each material depends on the characteristics of it. And that vapor profile will change based on where you're located. So if you're down deep in the south, maybe your vapor barrier will have highly permeable and non-permeable exterior air barrier. Whereas here in the north, we may want to have a vapor permeable outside. So it all depends on what the design is. So another example of air barrier training that you can see here is I have a hot plate here. And this is one of the examples I wanted to do live, but didn't have the ability to do it because of my current situation of being at the firehouse. But this hot plate here is a hot plate. It's at 81 degrees Celsius, which is pretty hot. I'm just going to boil this water here. The one on the left with the white membrane is a vapor closed peelant stick that has a glass disc on the top. And there is no vapor going through that material. The one on the right is a vapor open peel and stick from Suprema, and you can see that little bit of condensation on the opposite side of that glass. And that's showing in real life that vapor is going through that material. Now, our buildings don't handle hot water in the steam form very often, but that's kind of visual dramatization of what's actually happening through our building assemblies and materials. So the systematic approach to airtightness is that we are looking at a system, an air barrier system, but it's also a WRB or a vapor control, air vapor barrier. So this is by Polyguard. This is from one of the trainings that we did with the Air Barrier Association. So at the base sill there is flashing. Everything's done in shingle fashion in that it starts at the bottom and works its way up. There are pretty much no reverse laps, and then the water will shed around. The penetrations are detailed with liquid flashing or peel and stick. This is a vapor closed system, but it's a full system of an air barrier, which is acting as the water drainage layer as well in the wall system. This is a Tremco system. The Tremco system is a butyl-based vapor closed system. That's with the letters on it. And it's a systematic approach towards making the building, or in this case, the mock-up, air and vapor and water tight. We now have also on this slide, the gray membrane is a fluid applied, and that fluid applied is vapor open. So vapors can go through that fluid applied. Then here we have a 3M product. The 3M product on the right side with the clear is it's a peel and stick product that's vapor closed. It's an air vapor barrier. The rough openings are all detailed with their flashing membranes. The base detail, the inside corner, they're all done with their flashing membranes. And then the white membrane on the outside is it's a vapor permeable peel and stick product. So it's kind of like an STP applied onto a sheet membrane, and then it's put on the wall. So it acts like a peel and stick, but it's really like a fluid applied STP, which is being very common in the industry as a vapor permeable product. So these are the systems of many different manufacturers that do air barrier and WRBs as a part of their systems. Then we go back to Proclima, right? So Proclima's system, if you look at all the detail components, so one of the reasons I love to use the European kind of based air barrier systems is that you have all the tools and the tricks to make the building airtight, which will also make it more resilient and less susceptible to moisture in the end. So we have a peel and stick on the outside, the Hero, the Mento 3000 on the roof, all the tapes that are sealing every single joint that's going across, and then the auxiliary components, the Roflexes, the gaskets, all the other tricks that you may need to seal the system. Another systematic diagram from the Proclima system shows you all the components and how they work. So the Proclima system that you're looking at here is the intelligent membrane on the inside is the vapor control layer, and that vapor control layer stops the air on the inside where the air is warm, and then it'll allow the vapor to go through if the moisture in the cavity gets too high. So that's where it's Intello, it's an intelligent membrane. And the story that I always remember is that the intelligent nature of it, I believe, comes from the baking industry. Whereas you take a piece of bread and you put it into a bag, a paper bag, the vapor goes through, and over time it'll rapidly, get stale. Whereas if there were just a little bit of a vapor control plastic in there, it'll actually control the amount of humidity inside that bag where you're storing the bread and allow it to come out. And that's what they use within this system. A lot smarter and more science goes into it than just baking bread, but nobody likes stale bread or too moist bread. So this is an example of a house in the Pacific Northwest that's using the Proclima system to manage moisture. The Mento is on the outside, detailed out for the windows. It's got a metal roof, which is shedding the water from the outside. The Mento is a sarking membrane, a 3-layer TEF membrane that's fastened onto the building mechanically. It's a great product and system. And these are the components. So this is a little bit of the components from my work that make that airtight layer possible: the tapes, the membranes, the gaskets, and working clean and smart using primer and all the tricks and tools to make the building airtight, which airtight from the inside, watertight from the outside. A project I worked on that on the upper left on my screen is an older building. They did a renovation on the top 2 floors, the attic and the second floor. And then the next renovation was the bottom floor and the basement. So the upstairs was done, and then we insulated the outside with some wood fiber board. We coated the outside on the upper right with Mento, detailed out all the windows, and then they put on a rain screen system of the cladding, which is this, I believe it's a wood, I don't know if it's fiber cement or it might actually be cedar, but it's a fully drained rain screen system. This project's in Brooklyn, and it's a beautiful project. It did very, very well. And you can tell by the old architecture, the deep overhangs, that it's designed into it to shed the building from water. But the greatest risk in this building was interior moisture accumulating and getting stuck or trapped inside that wall, or rotting out the deck that would be attached to this building in the future. Now, on the other side of our work, the interior vapor control layer, we have another vapor intelligent membrane by another manufacturer, Partel, and that membrane will protect the inside from being exposed to warm air hitting the cold surface of this masonry structure. So if the moisture gets trapped in the wall and then hits the cold surface, it'll condense. And this is the systematic approach towards it. So the window bucks, the plywood, then get taped. You can put in, and then we blow dense packed cellulose in there. The black membrane that you see painted on the wall is their first version of their fluid applied air barrier. We used it in the rough opening. We used it on the party walls. It's airtight, the building, and went across. All right, how am I doing on time here? I'm flying by, right, guys? All right. So in these masonry retrofits, I have the first project I worked on was 88th Street. And we had a real world experience with this building, in that the top bulkhead had an exterior peel and stick membrane on the outside. So peel and stick, beautiful, asphalt-based, non-permeable. Vapor doesn't go through it. And then we came across this little electrical BX penetration that goes through there. That BX penetration got torn and put around. So I had to make the repair. When I made the repair, I was like, let me seal this on the inside and the outside. So I opened up the inside, and when I opened it up, I'm taking out the cellulose. And as I'm taking out the cellulose, there's only about 2 inches of cellulose there. I start to get to the outer edge of where the exterior of that wall is, and I could feel that it was wet and it was saturated. Like it felt different. Cellulose is normally dry, but for that last half inch, it was saturated. And it was that aha moment for me in that the air transport of hot, moist air coming in contact with that cold surface of that outside, then hit its dew point, and then condensated and then stuck within the first inch of that cellulose that was fully saturated, and you can almost feel the moisture in it. But the rest of the other inch and a half was dry. So the cellulose had the ability to absorb the moisture and wick it through to the outside. The Intello, as the moisture increased, it allowed it out so that it had the ability to dry out, wasn't trapped in that wall. So that's my real world experience with moisture as transport for that building. So the conclusion of the presentation is we need to look at buildings as a system, right? Stick with the system and go with it. Managing moisture starts from the bottom and works our way up in shingle fashions. And that the kind of like lesson that I'd really like to hit home really hard is that airtightness is just as much about shedding water and preserving of a building as shingle fashion and moisture on the outside. In construction, we're all feared of leaky windows and doors, but the airtightness and the moisture transport in a building can just be as risky in the rest of the product. So air barrier components require installed that they're drained. You'll need to address mechanical systems with airtight buildings. Understand how materials perform in an assembly subjected to different environments. The big kind of like debate in our culture is that North America is a really big place, and that there are climate zones are very different. So depending on where you are in that heating degree zone map, you may be really, really cold and have risk of condensation. You may be a moderate climate. You may be in the South where you have no heating degree days or very limited heating degree days, and your air barriers and systems. So you have to actually manage them and know where they are. Happy to answer them, but it gets very confusing based on geography. So yeah, I'll open up a wormhole there. So last one is building enclosures are important to performance and efficiency. So I'm Kevin Brennan. I am, that's my presentation. That's what I'm sticking to. I'm very lucky that my co-host or guest speaker here, Floris, is going to help us nerd out with his presentation, and then we'll be able to answer anyone's questions about moisture management or so. But thank you, everyone.
So yeah, we're going to look a little bit further, as Kevin had indicated. Air control is pretty essential. We like to do that on the inside to keep that humid air from getting into our fibrous insulation. And as we've been saying, if you can't keep the building dry or can't keep yourself dry from the outside, we're cold, we're uncomfortable, and the building will very likely fall apart. So, but we need to keep it also well built from the interior perspective. So there's what we're going to look at here is
the lead thing. Is it starting?
That the airtight is very important on the inside. For one, in the air quality, we don't want air wafting in and out. For comfort, if the drafts are uncomfortable, for durability, and of course for energy consumption. So why is this not advancing? This is, here we go. So the biggest tool we have in our toolkit is the blower door. The blower door doesn't lie. The blower door doesn't scream at you. The blower door doesn't get angry. The blower doors will just show to everybody on the job site where the leaks are and what needs to be fixed. And once we do a good job, construction workers actually understand this. If the second blower door, nobody's upset or offended. There's no super or architect or site manager that's screaming at them. We just have to find the leaks. So it's a very essential tool that we like a lot, because it will allow us to make our buildings very airtight, which will mean that they will perform as intended, and that the energy model actually will work, because we know we keep the conditioned air where it should be, which is inside the building. The second part of that is then, so now we have a good airtight layer. Now we have to assess our wall assembly. So Kevin talked about the dew point, which is a very simple rudimentary tool to assess if the dew point is in or out of the wall, but it's not very sophisticated. You can also use the glacier method, but it's a one-time snapshot, which has a couple of problems. It doesn't consider heat or moisture storage in the insulation. Wet insulation doesn't work. So if you have wet insulation, guess what? the glacier method doesn't, the graphs change. So it doesn't do this redistribution of liquid inside the insulation. And there's also no coupling of heat and moisture transfer in this dew-point glacier methods calculation. So it's not very helpful to predict if our buildings will stay dry. How can we assess this more accurately? That's with the Wolfie Pro model. So this is actually a computer model that does an hourly calculation and takes into consideration how the moisture and the insulation values and the vapor permeance of the materials change over time in these assemblies, over time based on what they experience, what happens with relative humidity, with the moisture, with the temperature. So, and with the solar radiation on the building. So it takes a lot of things in consideration. You will actually use the processing power of your computer in the right way. The computer actually uses this ridiculously high-powered input, processor that these computers now have. When I started doing this about 12 years ago, it would take a little while to get the Wolfie calculated. Now with the new computers, it goes a little faster, which is kind of nice. So we normally run 5 to 10 year analysis and see if these walls or roofs work well. And then we can see, do they stay below 15% moisture content? So they're safe, low risk. Below 18%, well, which is still okay for wood, but not for OSB. Plywood, maybe. 20%, it's kind of the danger threshold for us. Definitely don't want to go above it. And way above 20% is risks. Mold, rot, structural decay is pretty likely. So we don't want to design to the 20%. We like to stay below the 15%. Why is that? Well, then we have safety factor. Then something can happen. We can have a little leak in the air barrier. Somebody might hang a lamp, pierce our air barrier. It's not the end of the world because we have some drying reserves that we have some safeties. So moisture-driven damages, condensation, wood rot, corrosion, interstitial mold, and the freeze-thaw cycle can all be affected by this interior air barrier not being perfect. This is something to consider. Why do we need this perfect or almost perfect interior air barrier? Well, otherwise, the glacier method or the Wolfie calculation, they do not work. If there's air wafting in and out, these analysis tools have no value because there's so much air driving so much moisture into the wall. We cannot count on these methodologies anymore. So the risk is much higher. So what are the inputs in our Wolfie calculations? So the indoor conditions, occupancy, the air tightness, and the ventilation rate. So how much fresh air do we bring in or not? The dew point or or versus dynamics. So the temperature, the relative humidity, the wind. Is it wind washing going on, and the rain? If the outside cladding wet or not. And then the assumed embedded moisture after construction. We do want to make sure that in construction, we don't have wood moisture inside of our assemblies, especially not in flat roofs, because that could take a long time to dry out. So then we do these hourly calculations, and a lot of things go on here. The solar radiation, convection, evaporation, enthalpy. So you can see this is a very complicated calculation. That's why the processor has to work so hard. How did they define this then in Wolfie? Well, they did a lot of field testing, both at ORNL in Charleston and in Germany. So they actually calculated and made models to see what happens, and then actually check this against the real world data. So now we have a tool that actually can reliably predict how our buildings will perform. We also have to consider that, materials are not static. Here, what I said, your insulation value will be highly dependent on your moisture content of your insulation. Here you can see that thermal conductivity in metric. You can see how it depends on the water content of this insulation. And you can see that your insulation value actually, once it reaches a certain moisture threshold, the insulation value drastically is reduced, which again, then your wall doesn't work anymore, and it actually gets colder and colder and colder, which might mean that it condenses more and more and more. So intelligent vapor retarders, as Kevin also said, maximum protection. You know, we keep the moisture out in winter, but can let the moisture dry inwards in the summer. 13 perms in the winter, 0.13 perms with it if there is moisture in the wall and it needs to be driven out. So very vapor and open. So how does this, if we do this? Well, there's the calculation of the heat transfer and of the moisture transfer. And this is coupled back and forth. So it actually checks itself. So there's actually 3 equations going on and making sure what happens with the moisture, but then also with this heat transport and with the insulation values. So over and over again, more than 8,000 times a year. Of course, there's some challenges here, and that's where we're going to look at. There are a couple of projects here. So roofs are often vapor barriers, especially American roofs with asphalt shingles or flat roofs. So we don't want to have 2 vapor barriers. Everybody's always taught this, I hope. So if you have a vapor barrier on the outside, you shouldn't have a vapor barrier on the inside, but you can have a smart vapor retardant on the inside. Otherwise, the moisture could get into a small leak, but it would never be able to find the way out to the same hole. It would just bounce in there forever and cause issues like this. This is a SIP roof. There was air leakage between the seams of the SIP. It condensed on the backside of the asphalt shingles. But now it tried to dry back, but it couldn't find the hole back, the way back through the hole it came into. And so now the OSB got wet and you got mold in this asphalt flat roof, asphalt shingle roof. So maximize your drying potential. So smart vapor retardants, you see here every cycle, every summer, winter, you can see it can dry out. But OSB sheets or polyethylene sheets, they don't have the same inward drying capability. So now we have a Woofy model. So how do we check these roofs? Well, we check them in Woofy, but we also do some real life checking. So how do we do this? We do this with 2 methods. One is the OmniSense module and router. This is this little sensor here on the left. You can install in your roofs in any assembly, and it actually checks the wood moisture content and relative humidity of your assembly. The router then is connected to the internet, and you can get these nice readouts where you can see what the moisture percentages are. So then we can see what's going on after 1 year, 2 years, 3 years, 4 years, or 5 years. Eventually, it should be very boring, and we know it's safe, and we can turn off this system. So here was a really great EcoCore project in Maine. Flat roof, 14 inches of cellulose, Intello on the inside, but the flat roof is vapor close on the outside. And here we have 4 or 5 years of moisture sensor. And you can see there was a little bit of construction moisture. Actually, in the first year, you see that big spike. But then you see over the 3 eventual seasons, this dries inward. So this was, of course, not a great way to start. That they had some construction moisture in this assembly, but you can see the safety that this Intello system brought. And also that it was validated, because we saw in Woofy that it should work, that this cellulose can dry out over those next 2 years. So that's fantastic and good to see, and also with the real life validation. Here we have Minneapolis Climate Zone 6, good air tightness, passive house, versus index of 8 by Tim Ian. Good energy house. Walls are kind of boring, no Woofy needed because it's vapor open on the outside, so you can dry outwards. The SIP sheeting as the air barrier on the inside. It's a little bit vapor retarding, but open enough, so boring, we don't have to Woofy it. But flat roof, so same thing. Intello on the inside, little bit of foam on the outside to make the taper. 16-inch truss with cellulose. So what do? Well, we do a Woofy, but we also monitor this roof. Very nice airtight details. You can see the Intello over the interior walls already pre-installed, so the air tightness is continuous, and the Intello inside the rooms can be installed later. So here we actually use a very simple method. We have 2 screws, 1 centimeter or ½ inch apart, and we use a moisture sensor, an exact moisture sensor or RH monitor, and we just connect it with a long wire in the completed roof. And here we can actually see for this first winter, it's all, it goes a little bit in January to 16% moisture content, probably a little bit of construction moisture coming out of the wood. And Tim is actually supposed to get me some more data so we continue this for 1 or 2 years to make sure that this roof is working as we think it will. Here's actually the last Vermont timber frame project from 2013, and very good air tightness, climate zone 6 again, timber frame with foam-free flat roof. We had to push this a little bit further because we were pushed very hard by the building inspector that he didn't believe this would work. So we put some monitor sensors in there, and he eventually gave the sign off with a PE that we convinced this was a good idea. It should work engineering wise. Again, the walls are very easy. Get dry inwards, get dry outwards, some DB plus on the inside. But the roof, we did the same thing. Didn't use the OmniSense, but used the wood moisture sensor. And here we show in Wolfie actually that over time it goes, it's a little bit high up at 20%. And actually here we compared a dark roof versus a light roof. And you can see the dark roof dries much, much faster. You see after the second winter, it's already below 16%. Well, the light roof, you can see how long it takes to burn out the construction moisture. Of course, ideally you don't have any construction moisture or very little. So you don't have to wait that long to get dry. But here we can see actually the Wolfie was very conservative with the construction moisture. And over the years, it's below 10% moisture in this roof. So this is actually a very safe roof because they made sure they built it in a dry way. So that's my rapid fire 33 slides. I hope you enjoyed it, and let's go to the questions.
The question queue is lined up. And so Jeffrey, we'll kick it off with you. Let's go.
Okay, so Kevin, this one is for you, I guess. You had that great slide, by the way, of the 4 different ways that water moves through assemblies. I was wondering if you could just expound water vapor movement is okay in some circumstances. I'm just wondering if you could expound on that a little more about when, how much, and that kind of stuff.
And then you also had the question too, just about, what is a vapor barrier versus a vapor retarder, and trying to be clear of like what that perm number is before you go between both of them. I think that's kind of clear as well. So a couple questions for you, Kevin.
Sure. So, so there are two classifications really. One is a air vapor barrier, and most of the time commercial buildings, the air vapor barrier is on the outside, and it's either a peel and stick or a fluid applied, and a lot of times they're asphalt or based or so. Then we have the kind of like membrane vapor open materials that are either peel and sticks or mechanically fastened, and they tend to be like a membrane with some sort of texture to them that allow the vapor to go through them. So that could be Henry Blueskin, it could be Mento, it could be Adhero, it could be Sega's product. I forget the name of it. Somebody can help me out there. But each manufacturer has their different levels, and then they tend to be the vapor open membranes. The level that they're open depends on the manufacturer and the product, but I think it's around 10 perms or greater is considered open, and then they slowly get kind of like less vapor open. So it's really it depends on your climate of how vapor open you want it to be, and then are you doing exterior insulation or not. So the push towards rock wool on the outside is or wood fiber is a great pairing with the vapor open design. When we're taking a foam based product that's vapor closed and put it on top of an air barrier, it's then that vapor needs to escape through the gaps and the cracks and the drainage plane of the foam. So it's the assembly itself that gives it the whole thing how it's made. And then on a kind of like European or like our more common airtight, windtight buildings, they're designed to be more vapor tight on the inside for the majority of the year and more vapor open on the outside with the membrane outside. So it's the best way to get insulation to actually perform is by having it in a fully hermetically sealed enclosure or cavity that's sealed from hot, warm air on the inside and then wind driven air on the outside that is pressurized by wind and uncontrolled. So you don't get any wind washing. I do need to give a shout out to the podcast. The podcast had a great presentation about the thermal bypass. It's a great resource that's been put together, and it puts a little bit of like, oh, I trust the science of cellulose and densely packed insulation and other materials. I know I packed a lot in there, Jeff, but did I answer your question, or did I just, confuse
Yeah,
you?
no, I think you did. I mean, it's one of these age-old conversations. I always loves to hear other people's perspectives, and especially from an expert like you. One thing I've heard is a technique where you list the perm ratings of whatever your products are from exterior to interior. And if it looks like a V in terms of go down, 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 down to the minimum, and then up, 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 you're okay.
I think the manufacturers have a large play in here. Floris can answer this a little more, but I think it's 10 times. ProClima has a little stance on it. I think it's 10 times the permeability to be open towards the other direction or so.
It's yeah, you want to be, in generally speaking, for the heating driven climates, you want to be more open on the outside and on the inside. It doesn't necessarily have to be 10 times, but it's, you go in the wrong direction if you're getting more tight towards the outside. Then you might be letting more diffusion in on the inside than can get out on the outside at the same time. And then the main culprit in most US buildings is then the OSB on the outside, because now you have a nice old vapor break on the outside that's around 1 perm. So
in heating, so the guideline is in heating climates, you want to have most of your vapor open on the outside, and then in the cooling climates, you want it on the inside.
Yes, that's correct. You can in the cooling climates, but that for US construction is a little bit easier, because now if you throw your OSB on the outside, oh yeah, 1 perm on the outside. So that's okay. So as long as you have more vapor open to the inside of that, that's okay. Everything can dry inwards, because supposedly it's more humid outside than it is on your inside if you're air conditioning your building.
Fabulous. Thank you.
The mixed humid climates throw a little wrench in that, because now you have both.
I love the phrase that if you design your building perfectly, at some point in time, your air vapor barrier is on the wrong side of the 4 seasons. So you just have to manage your risk on your climate. But here in the Northeast, we're predominantly a heating climate, but in New York City, we have just as many cooling degree days as heating degree days. So it's kind of in between, but we tend to design towards the more heating climate, and there's less risk in designing a vapor open assembly, both to dry inside and outside. The more that we go to traditional peel and sticks and exterior insulation, yes, it's a perfect wall and it can be done anywhere, but the minute we put any kind of vapor barrier or vapor restrictor on the inside, stuff gets trapped in that wall, or if we start spraying foam on the wall, something's stuck in between, sips or other things like that.
No, good call. And I hope everyone saw the window picture from Hurricane Ian, where there was about 4 or 6 feet of water outside the window and the window wasn't leaking. And it just reminds me, we got to make sure we build our buildings so that all water can keep out of our buildings at all times. And sometimes when you don't expect water to find its way in, that you manage it properly, because otherwise it's causing problems. And as Mark said, we don't want our buildings turned into mulch. So, Jeff, great questions. And we got one more before we get to some updates from Kim. So we were heading off to Aaron Jones.
Oh, first of all, I realized that the real answer to my question is probably it depends. But there has to be a guideline somewhere with wall assemblies where there's this happy medium between where the dew point, the delta T, the condensation point, whatever you want to call it, and air tightness. There has to be a correlation there, because if water-laden air can't get in, there shouldn't be a dew point in the assembly, assuming you dried it accordingly prior to installation. But is there a point where one matters more than the other?
It depends on where it's leaking into. So like Floris pointed out in his presentation, if it's leaking into a roof assembly, that's a hot roof and it's got a cold surface, you're gonna have issues there. If it's
I'm going to stick to walls. I'm going to stick to walls because I'm still on the vent team of roof. Not saying it's right. I'm not saying it's wrong, but cold climate, vent till you can't vent anymore. That's where I live.
And the ventilated roof assemblies are great. You know, if you look at the Swiss chalet roofs of the venting just happens on the other side where we're normally used to, you know, like it's an air gap, it's a metal roof system, and those operate really well. Whereas our traditional roofs of venting the underside of the deck is kind of like preparing to fail, or when the moisture gets up there to ventilate it out. And I agree, it's necessary, but it's necessary in leaky buildings. If we can design buildings that are less than 3 air changes per hour, we have a lot less risk of uncontrolled moisture getting in other areas. The goal should really be 1 air change per hour. And then you have a lot more control over airborne moisture going into other areas. But at the same time, as we start moving into high performance, higher air tightness, and less heat being thrown at these systems, they don't have the drying potential that is needed to really dry those areas out. Passive houses are great that they have no cold surfaces, but sometimes that one cold surface, it'll show its ugly head, and that one thermal bridge will be the coldest zone, and then next thing you know, you got a moist piece of sheetrock in a door assembly. So interesting problems that you have small heat pumps heating and cooling the house, but there's only a little bit of heat being thrown at that area. Whereas when we used to have a 200,000 BTU boiler with steam radiators, that would dry out because we were throwing heat at it, but we don't have that same amount of drying potential anymore.
Okay, so 0.5 ACH 50 is not always the answer.
Tighter, build tight, ventilate right, I think is still the non-active or best, more craftsmanship than mechanicals is kind of where I lean towards. And air tightness and waterproofing take the same level of skill set. If it looks perfect, it is perfect. If it looks watertight and the lines are clean and professional, it should, yep, you know it. So
yeah,
it's bringing really what I think we need to do is we need to bring the trade and the craft of air tightness and doing proper waterproofing more mainstream and make it an attractive skill that carpenters want to put in their toolbox. It's something that, like, on a construction site, when I look at a carpenter and they're framing a house and they got their tool belt on, when I start having the nerdy air tightness problem, they're like, oh, that's what we have the apprentices for. And it's like, no, these are the details that matter. This is what keeps the building standing. So,
well, Kevin, I am a carpenter and I'm here and I'm asking these questions. So there's hope. Okay. there's other people like me out there. Yeah, we can get there. It's just not going to happen overnight.
Yeah,
Well,
fold them in and bring awareness, get technical, get nerdy. You know, just I joke around on the site that an air tightness guy needs to have the same attitude as a finished carpenter. It's either perfect or I'm not doing it. You can't tell me to hurry up perfection. I can't rush the details because otherwise it won't last. And, you know, finished carpenter, say doing cabinetry or fine millwork or whatever, tolerance is tolerance, and our tolerance in passive house air tightness and waterproofing is as close to 0 as we can get. So
cheers to that, Kevin.
Yeah. So it is now the top of the hour. So if you do need to move on to dinner, homework, whatever you need to do, if you're starting your day, you're closing off your day. If you got to go, you got to go. We get it. We appreciate you showing up every Wednesday. And of course, you know, there's homework to be done. You do need to bring a friend next week, bring more friends so we can have more conversations and collaborate more with everybody. So that's the homework. Now, just to kind of transition now from the main hour to the overtime, great to see that next week Jeremy will take care of the component spotlight Lamelux, and you can see, if you're trying to wonder why does Floris look so bright, that is because there's a Lamelux skylight providing him lots of brightness in that space, and always fill your room up with greenery. It does make your backgrounds look a lot better. So we got 2 more questions in the queue, and then we'll see where the rest of the evening goes. If you need to go, we'll let you run, and we're going to transition into the overtime. Mark, before we do questions, we didn't hear about you. Did you have any other insights about the technology, or the techniques that were discussed between Kevin and Floris? And then we'll get Mr. Peter Molnar queued up in the question time. But over to you.
I'm gonna pause my comments, Sean, just to stay on time, and pass my mic over to Peter. Take it over, Peter.
You're a gentleman, Mark. Peter, over to you.
Well done. Thank you very much. Yeah, Floris, hui prezentatie. That just wondering if the in the flat roof portion of your mention that that's what you consider your air barrier, your vapor barrier, so that inside there should not be another vapor barrier.
So on the inside, it's an air barrier, and it's a smart vapor retarder or intelligent vapor retarder. So we don't have 2 vapor barriers, because the inside is a smart vapor retarder. So it's closed when it needs to be closed, but it can open up if it has to.
Yeah, that's the correct way to do it. So you don't get mulch for rafters.
Yeah, yes, yeah. As you said, you should never have 2 barriers, because then the moisture will ping pong there and only accumulate.
Oh, yeah.
Yeah, no,
Thank you.
great question, Peter, because, you know, we, in past weeks, we talked about a red line test, but I think, Kevin, you, in your presentation that, illustrated from the graphic from the Building Science Corporation of, doing different line tests to verify the process. And so when we build a building, we want to manage bulk water is the #1 thing. And so I think it's poignant that you do a blue line test to make sure that water flows the way it needs to flow out, or, down and out, as both Joe and Steve Basic would say. And then we do the red line test to make sure that the air barrier is figured out. Then look at your vapor control layers, making sure that you've got the right layers in the right spot. And then figure out as much insulation you can afford to put onto your house. And ideally, minimum of 1 inch of extra insulation. Like I know Joe did this test that they proved that the dew point stays on the outside of that insulation for like most of the year. So now by that extra 1 inch of extra insulation, you have, really reduced any condensation happening on that plywood or OSB layer. And so just extra insulation does so much, just even 1 inch, just so much. So anyway, great question, Peter. And Doug, I don't know where you are, but fire on your computer. Doug, go for it. Over to you.
Hey everybody. Yeah, I'm in DC. So Floris, I was, like most people, I'm trying to get away from foams to avoid the fire retardants and the warming effects of the refrigerants and all that stuff. But when I read the 475 guide, which is actually really impressive, it did seem like very few roofs that I work on in climate zone 4, Washington, DC area are fully unshaded. And in one of our jurisdictions, we have to use cool roof technology. It's right in code. So I guess my question is, what are we finding in the real world? Obviously, we have to be conservative when we're writing a design guide, but are these things more robust than we expected, or a little bit, are they really kind of on the edge?
No, so this is where actually the climate specifics come into play. So, in this climate zone 6 in Vermont, we wanted to build, it was one of the first foam-free roofs we were doing. So we want to be very conservative. And so you could see that, the woofy with a lot of construction moisture in there, with a white roof was drying over like 3, 4, 5 years. So we're like, oh, it's a little slow. So let's not take any risk. We'll do a black roof, and because that dries in 1.5 years, so we're in good shape, But as you saw in that monitoring, that roof was never above 11% because there was no construction moisture. So this is also, and then the other thing is what we've done. We did in Philly, we did a roof where they actually had solar panels, foam-free roof, solar panels, which then the roof is pretty darn well shaded, right? So same thing, we put some OmniSense in there, and we did it, and actually it was interesting. And this is very, Wolfie sometimes a little bit conservative. We were getting some with cellulose, it was actually, this is always the interesting thing is people are like, oh, cellulose can hold the moisture and it's great, it's fantastic. But actually in Wolfie, it was like, oh, the cellulose stayed a little bit moist for longer. Same thing with the construction moisture in the Wolfie model. But then with mineral wool, it's like, oh, no, it's perfect because it doesn't hold any moisture, and it dries out fast. So in that roof, we actually monitored it, and the same thing happened. We were like, with cellulose, it was a little tricky with the shading, but you could already see this climate zone 4, it's much, relatively warmer, so longer summer, so more drying potential. And so we're like, oh, this is close enough, it was in our comfort level. So we said, let's do it, let's monitor it. And yeah, it's never a problem. So the further south, the climate zone 4 we are, and even climate zone 5, we know these rules are almost too strict, but it is because then it's, we have the golden rules, and it's like, if you do that, then there's, we know we're safe. If you break one of the rules, we kind of have to do a Wolfie to make sure we're still on the right side of the equation. So that's it's annoying, but that's why we have to we stay on the conservative side, and then we do a specific analysis, and we know it's right.
Excellent. And great question.
Just to point out, there is a line in the heating degree day map. It's that 4,000 degree line map. And I call that's the it depends line. Because your vapor barrier could be on the warm side, the cold side. And the honest answer is it depends, because your seasons are just so not fully in line with, north and south and hot and dry. So it's that kind of like Virginia, kind of down there areas, right pretty close to there. So,
and as Doug says, yeah, that line may go right through DC. Are you talking about separating some political views there, Doug? I don't know what you mean by that line. No, all good. No, and I mean, what's really nice is again, Floris, appreciate all the stuff 475 does with those real life testing, because for a lot of times we've relied on a lot of European products and European testing. And so to have stuff in North America that are looking at different climate zones and different, looking at different situations, and the fact that you invested in, testing methods that nobody can come back and say, hey, that's wrong. It's like, no, we put the test, here's the device, this is the results, and here you go, which is really fantastic. And, again, we're trying to rely on some trust. The fact that we have real life testing here in North America is great. So thank you for doing all that. And thanks to the builders and those clients that were willing to do those tests, because it's valuable stuff. And I know you've got more in the pipeline, which is great. So I'm sure in the next few months, we'll see more of those results. And next time we see Tim, we'll say, hey, Tim, give Floris more of those data. We want more data. Nothing goes wrong with more data. All right, Doug, we'll let you go. Thanks for sticking around to fire your question. If I missed someone's question, please let us know. Otherwise, we'll send Kevin and Floris home, because again, they're in New York, so it's already a little late on their time frame. But again, you've got some powerhouses here that'll answer questions if you're around.
Yeah, thanks, Sean. I got to run, but this was a great evening, and we'll see you in Chicago, right? So,
That's it. We'll see you in Chicago, Floris. Hopefully, the rest of us will be here with you. All right, Floris. So, thanks so much for taking time out.
See ya.
Thank you, Floris.
And as Floris leaves, I mean, it's really interesting about the whole roof color design, because I know in the whole sustainability movement, we thought, oh, let's get to white roofs because that'll help the reflectivity. But going back to the darker colors to deal with the heat to make sure that they dry out is really insightful. And I always think that's a bit of a takeaway. Enrique, fire away, my friend. What's going on? Turn over the microphone to you.
Hi. Thank you. I just want to switch a little bit to the weatherization or the retrofits that Kevin was talking about, because we're discussing a lot here in Vermont with the weatherization at scale. The coalition, we need to weatherize 90,000 units here in this decade, and that means 9,000 per year, and we're doing 1500s at this point. So what we're trying to do is how to speed up the process and how to, and whether there are some different approaches in doing that, and if there are different approaches, based on what are they based? So what are your thoughts there, Kevin?
So when you speak weatherization, I think of my original career working in weatherization, being an air sealing installer, but most of the homes were occupied. So most of our work was in the unoccupied attics and then insulating uninsulated walls. Whereas in today's world, most of the walls are insulated. So now our work then goes to the outside. And then so doing an exterior retrofit using vapor permeable materials coordinated with window replacements for that next level EnerFit step-by-step approach, I think is important. And if you have the ability to do a gut renovation and work from the inside, then you can use some of the smart vapor barrier, the smart vapor retarders like Intello or other membranes, and then do interior insulation. So it really depends on where your retrofit's going to happen. But most times in our areas that weatherization, the lowest hanging fruit is air sealing and insulating the attics and maybe changing the windows with the right windows and the right install.
Right. Okay, thank you.
Yeah, Enrique, that's a really good question. And just kind of a bit of insight here in Canada, we have Enercan that has been doing this national kind of research and communication. So now we have Retrofit Canada. And I'm really excited, and we'll talk more about things. But I've got a retrofit underway where we're doing 6 inches of rock wall on the exterior, and I actually really love this wall because it's now a 2x4 wall that unfortunately doesn't have the 3/4 inch plywood that I'd love to have it on the outside. It's got different layers from different times of how this thing has gone. But the fact that we're going to have more discussion about retrofits, because, we've kind of got 10 years or 12 years here in North America about really focusing on new builds, but retrofits are coming. They are coming fast and furious. And I also love the chainsaw retrofit that has been coined here, and how we can move forward, and the fact that we can focus on all of the techniques and the principles and the benefits that we've learned here, and we can apply it to retrofit. Because once you get rid of all of the, finishing materials and you get back down to the structural studs, that building is very similar to a new build. We just might need to figure out some of those tie-ins around some joints, because the form of the function, or so the form of the building might not comply. But it's really insightful to be doing one myself, to really look at things, and quickly it's like, oh, this is a new build. The wood's been there for 50, 60, 100 years. And now we're, working through those tie-ins, and so it's coming, Ricky. So great question. And again, go ahead, Mark.
I'm going to add to what Sean says. So, and this reflects to Kevin and Aaron's speak earlier, Enrique, is having the people that understand how the vapor is going to move through the wall are only as important as the people determining this discovery on the project itself. So when we're getting into that world of retrofit, what we think we're planning for, it's also responsible for conveying what we find out. Because that layer that you find in there that you didn't know that's in there, now you have to either work around or remove. And that's not an option to say we're going to forget we saw it, right? Because once you touch it, you own it. So that discovery has to be conveyed. That's why that team is important at the beginning of a retrofit, not just new construction.
Mark, to add on that, I think one of the key components of like weatherization and retrofit is almost like getting a master plan written down. So what is the plan or options for the whole building retrofit, like a deep energy retrofit plan for the building, and then figuring out what your strategy is on how you're going to implement it. Some strategies are a facade by facade approach, a room by room approach, front, back, or, you know, buy the windows that you can afford. Just do everything the best that you can afford at the time. Like a lot of the, you know, the retrofits in my middle class neighborhood happen based on the tax returns they're going to get that year. Okay, we can afford 6 windows and reside the rear of the house, or, you know, like, and then let's do it to the best of our ability. But what you have to coordinate is, what is my approach and how am I going to do it? And then what's my strategy? And that's really the key towards weatherization or deep energy retrofits. And one of the opportunities, I think, in our industry in weatherization is just like when replacing a boiler. It's like when the facade or the siding needs to be replaced, we need to tie those trades into our industry and then do smart things smart. And instead of installing a 1/2 inch of foam on the outside, let's install 6 inches of foam, because it's almost the same amount of labor. It's just a little bit more investment in it. And then let's put those windows outset into the insulation layer. Let's flash them properly where it might be easier. So I think those staged retrofits are an opportunity. And then hopefully with more of the Inflation Reduction Act funds coming online, working in a great state like Vermont, if VEIC can work out how to get mass or better incentive programs to the people that are out there. I know one of the holdbacks in my market in NYSERDA land is like, back in the day when I was in it, they wouldn't incentivize replacing siding, you know, so like you couldn't put it in the program because it was a facelift. But if you could roll it in, and when I'm redoing my siding, the windows and insulation and air tightness at the same time, then that SIR comes down. You know, it's a part of the master plan, because I can't just put insulation and not have siding on the outside. It's a part of the package, you know, so hopefully that gets worded. Enrique, I hope that helps.
Yeah, but could you develop some approaches based on typology of buildings?
I am a big typology fan. So Cape Cods, row homes, you know, just the same way I attack a building, there's a strategy and a plan to implement it. And if each neighborhood and municipality has 6 different building types, you can have a retrofit plan inside, outside for each one. You can have a facade by facade approach, you know, so understanding how the building was built and what needs to happen to get to it, and then what your options are, I think are good. You know, like the Cape Cod type house is it's a very difficult retrofit in that way the attic's done, and there's tons of case studies on it, weatherization, home performance. But that same approach, if you did it on the outside, could be game changing. And now that you're not insulating eaves and you know, knee walls and other things like that. So just something I know about some of the typology in the Northeast Vermont area.
Yeah. And before Mark jumps on, Enrique, just to plant a seed with you, Butterwick Construction in Edmonton, his name escapes me, but that particular gentleman is doing panelized retrofits, the first in North America, again, taking the, you know, the Denmark energy sprung approach, and Enercan in Ottawa. Those 2 examples are just really great process. And he's built about 6 to 8 of them there in Edmonton. And you're right, going wall to wall, but you know, new build or retrofits, if you don't have a plan, you are done like dinner, because your new build is working on like that. I say 52 weeks to 74 weeks of construction, where your retrofit might take 2 years to 10 years. And if you don't have the right plan, you're just not getting anywhere. So
the plan is something that I am trying to introduce here, because for me it's a basic tool. Yes, in order that every step that you take along the way is not going to be a roadblock for the next step.
Yeah,
but in terms of the panelized, that's something also that I wanted to introduce here. But people here have been kind of reluctant to think about, because I mean, it's something that's still years away, maybe from Vermont.
Well, guess what? It's happening in Edmonton, and it's now, he's near 2. So Vermont could happen in 6 months. Just copy and paste what's happening in Edmonton, and you'd be surprised of his approach And again, he's open source and making collaborative. You could literally call him and say, come do the presentation, and he's not going to fly. He's just going to put up his laptop and speak to you from Edmonton and hop into Vermont and tell you what it's like. And I can't believe I forget his name, but
Well,
anyway.
if you remember it, I would.
Don't worry, I'll put in the chat here as we switch. Mary has a question. So Mary mainly, should be really to Floris, but I know that Mark, Kevin, and myself, the three of us will answer this question. But Mary, go for it.
Okay, so I'm really interested in learning on how, what are the steps for someone to learn how to do Wolfie models? Is there college classes? What are the steps for a person to be able to do that?
Floris might be better off answering this question, but there are some training that happens at the Air Barrier Conference. I know that there's a Wolfie modeling class there. On the other side of I think that if you took the Passive House consultant training through FIAS, they dive into a decent amount of Wolfie Pro modeling, and there are some extra level classes at the Passive House conference with Wolfie Pro as an add-on workshop at some of the conferences. So a lot of the training happens at the conferences, the Air Barrier Conference, the Passive House FIAS conference, and then there might be some North American Passive House network Wolfie training that happens as well. But
so on average, what is like the cost that usually people end up having to pay to be able to, be able to do that? I mean, because for me, I'm in the Pacific Northwest. For me to travel is really hard. I've got kids. I'm taking care of the last grandparent that my kids have. So a lot of things I do are from home.
Yeah, I'm not sure there is a virtual training for that currently. You can take a look at it. But like everything during COVID, everything came online. So there should be something out there. I know I personally haven't taken any of that training, but.
Okay, thank you.
It actually, Mary, so this is the great thing about this community. All these questions are perfect. So FIAS offers a virtual Wolfie training. Leslie just put that up. Someone will probably get that link, but that's really great to see. So there is.
Mary,
I'm guessing it's probably $2,000 to $3,000. I don't want to underbid it or overbid it. But there you go. And all those folks are, what is your background, Mary? What is your profession?
My dad had 5 daughters and I was his son.
Got it. Okay, well, that's skill. Okay, so you'll find in the Wolfie world, a lot of engineer-based thinkers are in that. That's why I don't do Wolfie training. I rely on engineers. So you can see the links here. And if you go to the bottom of the chat in that corner, those 3 dots, that will allow you to copy all of them. And you'll find these folks pretty remarkable. There's probably a number of designers and consultants on this call here.
Mary, the other opportunity I would say would Passive House training at BCIT. That's phenomenal training right in Vancouver. And then Southern Seattle Community College, I believe, has a building science program. So those are Pacific Northwest kind of like easy, accesses. And then hooking up with them, they keep the travel time down, not going bi-coastal or so, but the resources are out there.
Yeah, I'm having opportunities that have come to my attention, and I'm realizing that Wolfie is definitely of interest, and that if I can be able to bridge the gaps, between what it is that I'm already really good at versus what I don't know as much about, that someone's pointed out some opportunities to work from home that would be very beneficial.
Yeah, 100%. Again, thank Leslie and Devin for putting those in the chat. And Mary, I have to say too, now with the different grants out there, is the price of these courses shouldn't be a hindering. There's somebody out there that can give you a grant and give you money. You just might have to find for it and lift up that big rock and find that bit of seed money, because people need your skills and your passion and your ambition. And so if you're interested in taking this course, there's probably firms where you can get hired on and they'll pay you to take it because, you know, you having that passion saying, I want to take this, please, you know, please, there's people out there. And if you can't find them, reach out to the three of us. We'll find someone for you because, you know, again, there's 35 people on now, but earlier there was 86. And I'm sure there's someone that would be wherever you are in the world, we want you to do this. And even talking with the team at 475, I mean, they've got a couple people that do this, and I mean, they could want more. And they were at one point using someone out of France to do this modeling for themselves. So you'd be remarkable how small the world is. And if you're interested in taking this course, more of this modeling is needed. So you could take on that course and put yourself in a very niche market that is very desirable. So thank you for being interested in it and enjoying tonight's presentation, because we did get technical, we did bring the technique, and of course there's lots of technology. The 3Ts were in full effect tonight. Gentlemen, I think we got through the questions. Mary, thank you for asking the last one. Oh, sorry, Aaron, before you go, Enrique, I had to look it up. The power of the internet is great. Peter, and it's funny, I always think it's Peter Armageddon, but no, it's Armagon, and he is an unbelievable gentleman, super interesting. He should be retired, but he loves this so much that he is retrofitting all of Edmonton. And fun fact, folks, there is more net zero homes in Edmonton than any other city in North America because of two people, one being Peter, another one being Mr. Nazira, who just wants to push the barrier. So again, a bit of passion and a bit of desire, and you can literally change cities. So fun fact about Edmonton.
Just throwing this in there for Enrique. I don't know if they still exist, but there used to be some timber framers in Vermont that produce their own SIP panels. That might be a resource that you could try reaching out to. I'm not saying it's the answer, but it could be the start to an answer.
Yeah, you're probably talking about new
works.
New works, yes. So for Jacob Buisman,
Yeah, no, it's new frameworks, I think.
new frameworks, yeah.
Yeah, actually, I have somebody's business card from there just here in my thing.
Yeah. No, we are in contact with them, yes. And that's one of the options, yes. I would like to introduce the panelized weatherization. That's something that the people here still don't get it, don't understand. So we'll have to rework the existing wheel.
Just Enrique,
There we go.
you did some more oil.
Jacob Diva Rakusin.
Yeah.
And he's
Good friend of mine, yes.
Yep. Enrique, we have to talk. I have a house in Montgomery Center, very close to you.
Okay. Anytime you're here in Vermont, let me know.
Because Jeff, you were saying too, so how many walls on your house have you retrofitted, or you're still in the planning phase? I apologize. I know we've talked about this a few times.
Who, me?
And you.
Well, we have a house in central New York that I'm still working on my wife that we need to do, but yeah, so there's that one, and I still have to do the thermal bridging analysis on it, but it's a 2x6 construction with 1 inch of rigid on the outside. So we're going to replace the siding, and when we do that, the question is, what do we do?
Thermal bridges are overrated, Jeff. Don't worry about those things.
That's well, I heard that continuous insulation solves all problems.
A nice wool sweater, just a nice wool sweater for the house.
Just like my mother said.
Yep.
Put on a wool sweater. That good Scottish response.
She also said, change your socks, put on boots, wear a toque, and don't forget your lunch. So we can't stick to one small statement.
It's best. That's what we can stick to.
Yeah. All right, everybody. Well, I think we've got all the questions answered, or at least we've sent you down the path of some type of resistance to carry on with your information and your research and all that stuff. Kevin is sharing something. Yes, that is the gentleman. Oh.
Go for it, Kevin.
Nice water barrier. I like it.
If you wondered where the photo came from today,
There you go.
the team.
You gotta tuck your jacket into your pants and your pants in your boots, right? So that the water all pours in.
Good flashing. Yeah.
Yep.
See, the
And your
best part
house
was,
will- your- one last thing. Your house will smile just like Kevin did.
yeah. The thing is like when he does this stuff, he doesn't realize Mark and I are saving it for later so that when we need that bit of information, it comes back at a good time, you know?
Kevin has videos of me for 10 years ago. He keeps throwing in my face, so that's all right. I do want to do some acknowledgements here.
Yeah.
Since we went through questions and we're all in the overtime. Anyone going, 2 parts. Anyone going to FiesCon, buy Floris and Kevin a drink for presenting tonight. It could be water, it could be iced tea, but you know, give them a cheers. And then I want to say to my buddy Aaron Jones, who got the great blower door score the other day and gave away a RetroTech blower door with some of his manufacturing friends. This kind of competition that you started is something I've always wanted to see, Aaron. I'm glad you took it on.
Honestly, it's like, why can't it be a competition? Like, really, like, let's make this a real thing. Like, something you talk about on, you know, Saturday when you meet for breakfast with the boys. Like, no, man, 0.47, bring it.
Aaron, I've talked about it for years, and I think I just haven't had enough steam behind it. But annually giving out the Golden Blow a Door Award for Passive House Accelerator, the tightest project per building type, one for multifamily and one for single family, and then show us your blow a door score and what your air tightness numbers are. We may have to go to permeance numbers as opposed to ACH to really differentiate. But I don't know if we need to get too nerdy. But if we can get something together, I think it's always fun, because the reason I got into Passive House is because I've always asked, what's the tightest blow door number you ever got? My first go at weatherization, it was like, oh, you can't go below 1500. We'd have to install ventilation, and that's not in our budget. And I'll be like, but why? They say seal tight, ventilate right. We can do better. We can get down below that number. Let's do better. And that was the exciting part for Passive House. It's like, those blow door scores are off the charts. Those are really tight buildings. They must actually really work. And then once you experience them, it's cool. But
so Kevin, if we were to rule out the ACH and we were to talk about the CFM, how would you weight the size of the building, right? The window ratio, the height of the building, the whole cubic, because let's face it, thank you, Jeffrey. There's gonna be some real battles here. And I see Norm thinking about it. You could read people's faces. How would you weight this?
CFM per square foot.
CFM is awesome, but really the whole point is, if you can get people engaged to the point where we're willing to battle about how we determine this number, we're winning.
Oh yeah.
Either way, but
We're winning.
CFM per the square foot normalizes the size per square foot of enclosure, normalizes the size of the building. It's geeky. I get that.
I'm saying that's not enough, Jeffrey, because if someone does double hung local windows and it's the exact same volume as the person next to them that has the triple pane fixed windows, then I say I don't care, because that person with the double hung gets the award because they really dealt with the air.
The debate continues.
But that's part of the point, though, right? Like, if I'm sitting here at 147 and Mark shows up at 147 and Mark says, well, yeah, but you cheated. You got triple glaze. I've only got double glaze. That's where this comes. we're
Well,
going places.
In that case, Aaron, you guys would be the tag team champions of the world, and you guys can fight it out internally. But that's a pretty good number to have. Share the belt for the
So
season.
I will commit to talk to Harvey, and we'll figure out how to get costs per square foot, cost CFM per square foot of enclosure, or cost per ACH, something there. But the debate continues.
Oh, and then we'll go with like, well, I have a glazing rate that exceeds 50%.
Who cares? Who cares what the glazing rate is, as long as it's tight?
Ronnie's chiming into right. The
Go jump in, Mary. I'll hold them back for a minute. Go ahead.
Tight is right.
I was just gonna say, change them a sign, T to a flat B, too bad.
Awesome.
Let's add some hand action to this, some trash talking. Too bad.
Awesome.
That's it.
Ronnie, chime in. Go
I'm
for
sorry,
it.
I'm sorry.
Yeah, Kevin's going.
So for someone who has built a few
Shorten after
net
that
zero
sign.
homes or passive homes, it's not about the glazing of the windows. You got to install those units right. Sure, it's great when you have triple glazed windows and triple seal, big advantage, 100% versus a double pane, double hung slider, right?
Yeah.
But if you install those windows wrong, no matter which one, you're gonna have major problems. You're gonna have the right applications, the right tapes inside and out, and you gotta flush them out properly, seal them up. That's the key, and that's why those low numbers. I've built a few homes in my life, and these last few ones that we did with the Mento on the outside, with the Intello on the inside, with the bright profile tapes on the windows, and the expanding gaskets, that's a game changer.
Hey,
Really.
Ronnie, where are you based?
Where am I based? Ontario, Canada.
Awesome.
Ontario. Well,
Yes.
we
An hour
do-
west of Toronto.
west of Toronto. We do not have enough projects. We do not have enough projects from Ontario. So you see these fine folks here. Please bring your projects to the show.
I will try.
Zach at passivehouseaccelerator.com and just put in the subject line, Kevin said I can do this. And then
Okay.
you're sure to be in.
Hey, Ronnie, do you know Harvey Minnick?
Do I know who?
Harvey Minnick.
Hey, Toronto's a big city, It's not like, oh, hey. So
I don't think I know Harvey, but I mean,
You should.
yeah, he should. But Jeff, just remember, 60% of Canadians live in that panhandle of Ontario. So, and the rest of us
sure,
are
for sure.
along the 49 parallel. So, if Ronnie doesn't know Peter, who are here in the same room, then you know that Ronnie doesn't know Harvey. So we'll work on that.
There's room for improvement.
Absolutely.
No
Ronnie,
said.
joining us, and again, great comments, and again, great to hear that your 1,800 square foot build did pretty well. So bravo to you, and thanks for showing up here tonight, because
Awesome, man.
that just
You're welcome.
means you're now setting the standard for you and your market in that area, and so people are looking up to you. And I mean, this is the best part is, we have elite builders and collaborators and contributors here every night, every Wednesday. And it's a question of what our ripple effect does in our local municipalities and counties and countries and everything else. So love it all. Again, it's great.
I'm also excited.
Yes, Paul is correct that LA is the 5th largest Canadian city.
that
Mainly
you-
Gretzky came to town. That's all I have to say on that point.
The other interesting part that I like about what Ronnie brings up is it's an 1,800 square foot residence. I love that size. I love that size and smaller. I'm not really interested in these other buildings that can hold 11 people, unless there's 11 of you in the family, then awesome. But awesome to see the 1,800 square foot. I like that square footage a lot.
Yeah, it's interesting. Again, we could follow up with Brennan, who was on our show a few weeks ago, talking about, sustainability is all about zoning, and the more density we can do helps a lot of our issues. And even though we're trying to change a lot of the climate change by the walls and the assemblies we're doing, but the zoning would definitely help out with density issues. So, hey, but at least tonight we talked about moisture management. It was the theme of the month. Kevin and Floris went deep into the woods, into the thickets of it all. And anytime that we can dump water on Kevin, even if he's protected or not, is a great day. And I think we had a lot of fun this week with his visualization of him wearing his suit. So Kevin, again, we're lucky that you're a guest host tonight. You're a co-host every week. We love what you do. We love who you are. And I can't wait to see you in Chicago in a few weeks. So for those that are making the trek to Chicago with FiasCon, thank you for buying your plane ticket, because I'm still haven't done it yet. And I know if I don't do it tonight, Kevin's going to get mad because he really wants. And again, if you don't have a room, realize that Kevin, Mark, and myself are creating, again, the legendary frat house at a Passive House event. There was a Canadian version in Pittsburgh. There will be a North American version in Chicago. So if you're down and out and you don't have a piece of floor or a bathtub or a closet to sleep in, let us know. We will find you a piece.
And I believe a professor, if I had this right, and I don't even know if Kevin knows this, I believe a professor from George Brown College in Ontario will be joining us as well. So there was a certain sponsor that helped made that happen.
More about that next week.
Next week, we got a great show. Tomorrow, I believe, is that Jeremy speaking tomorrow? Do I have that right?
Next Thursday.
Oh, next Thursday. If y'all haven't signed up for Jeremy, he's really good. He works with Floris over there at 475. You're going to enjoy Jeremy a great deal. Make sure you sign up and share that link with other folks, because not everyone hears about this. That's your duty.
Yep. Pass it on. Make sure they're available. Kevin, any final words from the firehouse?
Nope, everything's good.
Awesome. Well, hey, again,
Thanks,
glad
guys.
it was calm night in the firehouse. You could join us, and everyone else that's here. Safe travels. Be well. Thank you for joining us. Share, collaborate, and learn, folks. One thing we can do. Keep it going. Have a great night. We'll see you sometime soon.